Okay, so today's lecture is going to be about lower bound using the ETH or strong ETH, known as SETH. So, as background, let me talk a little bit about maybe the most important problem in computer science, which is of course whether P is equal to NP. So, the problem with this, this problem dates back to 73 or something like that. So it's by now close to 50 years old, and I think it's fair to say that we are very far from being able to resolve it. And I think the problem with this question is that it might just be the wrong question, right? The answer, as far as what it tells us about computing, can be useless for both possibilities, right? So let me show you two scenarios of answers for these questions that might be true, and both of them are in some sense not helpful, right? So the first possibility is that in fact we can solve 3 SAT so answer 1, let's call it. Answer, let me write it again. Answer 1. This would be P equal NP, right? So the first possible answer, as far as we know, is that not only P is equal to NP, but in fact 3 SAT can be solved in linear time. That would be, this is extremely unlikely. But it can be solved in linear time where the constant is terrible, right? So think about linear time, but C of n, well, n plus m, right? Where n is the number of variable and m the number of clauses, something along this line. But the constant C is, C is equal to, let's say, Ackermann 10, or Ackermann 4, let's say even. So what is Ackermann 4? This is this Ackermann function. So, I'm not going to go into the precise definition. It's just a way to write terribly large numbers, right? So Ackermann 4 is something like, depending on the definition, there are several definitions, but it's 2 to the power of 2 to the power of 2, a tower where the number of such things is 2 to the 16, roughly 64,000, roughly, right? So, so this constant is bigger than the number of atoms in the universe. It's bigger than anything, essentially, by, not by order of magnitude, but by order of orders of magnitude, right? It's a ridiculously large number. The strange thing is that those Ackermann functions somehow naturally appears in the analysis of algorithm, which is kind of shocking. But anyway, if I give you a linear time algorithm that works in this time, this is completely useless, right? We cannot even solve an instance with input of size 1 or 2, although, this is linear time algorithm. So all of NP is equal to linear time algorithms, but in practice, it doesn't tell us anything, right? So this is one possibility. And the second possibility is, of course, that so somehow this is the answer that would be most useful, but it's not. But let's go to the other possibility. Answer 2, which is P is not equal to NP. And in this case, 3 SAT can be solved in, some ridiculous time, right? So ridiculous but good, right? So n to the log star of n. If you don't want log star, let's say log n. Okay. In fact, log n to the power log n is already pretty good, by the way. Right. So, and here let's assume the constant in the O is very small. Okay, like 1. Right. So if we can solve 3 sat, you know, maybe n plus m. Right. So if I can solve 3 sat in this time, you know, this is not polynomial time, so this would in fact imply that p is not equal to np. But on the other hand, this implies that we can solve 3 sat efficiently because, you know, log n to all practical purposes is a complicated way of writing 5, right? So for all values of n that are integers. So this is really something like n to the of 1 in practice. Okay. So the answer, you know, the answer for p equal np can either be positive, negative, and in both cases can be, you know, can be useless, right? You know, can mean the other direction that we really want to the implication to be. And I think the reason for that is that this problem is very unspecific. It's very wide. It's very unspecific, and that's really why we're having such terrible difficulty in making any progress on it, despite, you know, almost 50 years of trying really, really hard, right? I think it would fair to say that p equal np is now one of the hardest problems in math as far as, you know, the amount of human effort that went into understanding it and solving it. Okay, so how do we continue from there, right? From here, right? So people tried a lot of things, and you know, literally every 2-3 years somebody comes with a new angle on this problem, and people come with approaches, and then usually turn out to be a dead end. And of course, modern complexity is a very sophisticated field with a lot of deep math, and there were some, you know, very important results over the last 50 years, right? We understand much better hardness of approximation, PCP, stuff like that. Okay, but from the algorithmic point of view, what people started doing reasonably successfully is come up with conjectures which are way more specific. Okay, so let me mention one such specific problem, threesome. So threesome is the following pretty innocent problem. You have a set of numbers, you have a set of real numbers that are, okay, so in fact there are several versions, doesn't really matter as usual, but let's take this version. We have 3 sets of of real numbers. Let's assume that they are all of size n. And now we want to find a triplet that add up correctly, right? So there is the question is there A in A, B in B, and C in C, such that A plus B equals C, right? Okay. So this problem, if you think about it, without too much thinking, can be solved in n squared log n time. You essentially try every pair of numbers in A and B, and you do lookup in C using, let's say, binary search after sorting C. But in fact, if you work slightly harder and you can think about how to do it, you can do n squared time. Right? Essentially, you can be a bit more clever about things. Okay, so the threesome hard conjecture is so this conjecture believes that so this conjecture says that we cannot do any better. Okay. I don't know what's going on. Let me try again. Right. So this conjecture is that any algorithm for 3 sum requires n squared time. Okay, and well, one nice thing about this conjecture is that we know it's false. So using bitology and so on, you can get algorithm with running time n squared over log n. Okay, so using bitology. By bitology I mean tricks about bits and encoding problems in words and so on. But essentially the belief is that up to polylog factor, this is correct. You cannot do better, right? And then you can, once you have this conjecture, you can show a lot of problems are equivalent to this problem. Things like, maybe my favorite problem, one of the favorite problems. I give you the unit square. I give you the unit square. I give you a bunch of triangles. Right. I give you n triangles. Are they covering the square? Right. So this is a natural question, and this problem is some hard. It cannot be solved better than quadratic time, and so on and so forth. Right. There's a big collection of such problems nowadays. So this conjecture, I think, by now, the Trisam-Hart conjecture, I think, is 20 to 30 years old and proved quite useful for certain problems. And there are other similar conjectures, right? People, as I said, except for maybe speeding up a polylogarithmic factor, we made no progress on those problems. Okay. More recently, people started looking on this conjecture related to SAT, or if you want, 3 SAT. So think about the SAT formula, so 3 SAT formula, and with f variable. Okay. So intuitively, the naive thing is you can check all the possible assignment, and you spend n plus m time. Right, this is the naive algorithm to solve 3 SAT, but in fact you can do slightly better, right? So there is some constant, it's I don't know, maybe half or something like that, where you can do, right, there's some constant, it's bigger than 0. I think it's roughly, currently C is something like half. I don't remember the exact value, it doesn't really matter that much. So by being very clever, you can do better. And I think, in fact, it's a randomized algorithm. I think the best algorithm currently known, right? The idea, for example, is that you start with a random assignment, and then you find a clause that doesn't hold, and you take any variable in this clause and you flip its value. Because one of those variables, need a different assignment, so you randomly guess one. And so for 2 SAT, this heuristic get, in fact, quadratic time algorithm. For 3 SAT, it's much less efficient, but it still gives you better than 2 to the n algorithm, right? So, so the way to think about it is that this is essentially still exponential, right? The running time is, the best algorithm, for SAT, 3 SAT is essentially exponential. Now, I should say, by the way, that this is true, by the way, for a lot of NP-complete problems. In practice, we know how to do much better, right? So there is a huge amount of work on 3 SAT solvers, and in practice they do very well. And for large fraction of formulas, 3 SAT formulas you get in practice, they solve it much better than exponential time. Now, all the 3 SAT solver we now have in practice, they all suffer from the problem that in reality they are, there is always a bad input for which they take exponential time, so it's not like we have even a candidate to solve 3SAT in sub-exponential time, but in some sense, it does mean that 3SAT, that SAT or 3SATs are probably in practice not as difficult as theory suggests, for what it's worth. Okay, so the question, of course, is, if you think about it, can we do better, right? Can we do much better than this algorithm? And the at-edge conjecture is that the answer is no. So this is exponential time hypothesis. Okay. So the exponential time hypothesis is that there is a constant C, there is a constant C such that larger than 0, such that any algorithm for 3SAT requires 2 to the Cn time. Okay. Now, notice that this is an extremely strong conjecture, right? Because, as I showed earlier, this really says that what we know about 3SAT currently is up to maybe small constant is the best one can hope for. Now, the one thing that one needs to remember is that here's what the running time classes we have currently, right? We have polytime, right? And then we have a lot of other classes that we are not very familiar with. And then we have this, let me call it 2 to the C of n, right? This is where essentially exponential time starts. Right. So we have polynomial time, then we have this huge gap. We have let's call it the swamp. And then we have exponential time. And there are a lot of running times in between, right? So, in fact, I showed you one of those running time in between for like n to the power of log n. Or, you know, so in fact, I know algorithm with running time n to the log n. So it's not impossible. What's more common is n to the polylog of n. Right. So this is what's called quasi-polynomial time, QPTAS. Quasi-polynomial time, QPTA. Okay, so this is quasi-polynomial time, and intuitively, if we find a quasi-polynomial time algorithm for a problem, it really means that we believe that it's polynomial time solvable. It's just a strong indication for that. So you know, so for example, relatively recently, it was shown that graph isomorphism is quasi-polynomial time, which probably means that it's polynomial, and so that's interesting. But the thing to remember is that there are a lot of other running times here in between. This gap is huge, right? And to see how big it is, don't look on the running time, look on log of the running time, right? So if you look on the log of the running time, what we call polynomial time is really O of log n, right? Because log of, you know, this is log of n to the O of 1, right? Polynomial time is logarithmic in this log scale, right? We are now in the age of exponential curve and log scale curves. So this is a good thing. So a quasi-polynomial time, right, is essentially polylog, right? Then there are things like sub-exponential, which I didn't even mention, which is, running time of the form 2 to the square root n, right? Which is of square root n, right? And then in the higher end of this curve, this thing, we have exponential time. Which is, in this curve, it's just linear, right? So this is really the scale, and this is the gap, right? And the gap between log n and n is huge, right? This is really a monstrously large gap. And what the exponential time hypothesis says is that SETH is here. Or 3 SETH is here, to be more precise. Okay? So first I should say that I don't believe in the exponential time hypothesis. I believe that it's much more likely that 3 SETH is in fact in this class, the sub-exponential time. And my reasoning is because there are some NP complete and NP hard problem for which we have a sub-exponential running time. Okay, so for the last 20 or 30 years we were not able to improve the exponential time for 3 SETH, but this is only our collective stupidity, and if we have to be conservative in our guesses, it's much more natural to assume that it's the best running time of 3 SETH is somewhere in the swamp. It shouldn't be in the higher end. But this is just a wild conjecture, and in fact, assuming that it's exponential time is it's a completely reasonable assumption, right, or a hypothesis considering what we want, and I think in fact, and it has the benefit of being very specific, and this is why this hypothesis is so useful. It's very specific, which means that suddenly we can go into polynomial time and get lower bounds for regular problems in polynomial time, right? So in recent years there were a lot of pretty amazing results. Maybe one of the cutest one is that edit distance, right? Edit distance requires quadratic time under ETH. Right, which is kind of amazing, right? Because what this statement says is that if we can do edit distance in subquadratic time, then we can solve 3 SETH faster than exponential time. So a very surprising result, and in fact there is a big zoo of such results by now, right? And the reason why we can derive such results, those conditional lower bounds that we could not have done before, is because this conjecture is so specific, right? It really tells you this is the running time, and you can really not do better than that, which is very very nice, right? And I think in some sense, you have to think about when you think about lower bounds, you have to think about it in a very different way than algorithms. So when you prove lower bounds, in some sense because we didn't succeed for so long to do anything really useful, we don't even go with we don't even go with the conjectures we believe are true. We go with the conjecture that we are not able to disprove at some level, right? So we are not able to disprove at the edge, so we say, okay, let's assume it's true and see where it leads us. So it's in some sense similar to the old saying that you go to war with the army you have, not the army that you wish you have, or in more modern take, you go into a pandemic with the administration you have, not the administration you wish you had. Okay, so this is the exponential time hypothesis, and we would like to see some lower bound that follows from that. And the second version of it is called the strong exponential time. So this is SETH. This is strong. Strong exponential time is thought as this. Time hypothesis. So what this conjecture says is that, and I will be very specific here because I don't want to say something incorrect. Right, so this says the following: QSAT, right? So this is 3 sat per Q, right? Every clause has exactly, you know, I have to up to Q variables, or Q literals to be more precise. QSAT cannot be QSAT cannot be solved in time 2 to the delta Q of n time faster, right? So it's the same as at the edge, right? You cannot solve QSAT in time faster than this, but the conjecture says that this constant delta of Q, right, the power, the constant in the exponential, this goes to 1 as Q goes to 1, Q goes to infinity, right? So essentially it says for clauses larger enough, you cannot do better than 2 to the n, period. There is no constant, you know, the constant is just 1. So I should say something about SETH. So SETH in fact is widely believed, you know, I have to say it's probably less correct than at the edge, right? They are both hypotheses, so that's a bit of a weird statement to say, but I would say that this goes in the wrong direction of the intuition, right? Because SAT intuitively becomes easier if the clauses are large, right? So in particular, if you have you know, you have m clauses in a formula, right? And every clause has, you know, omega of log m variables, right? Then it's not hard to show that a random assignment satisfies the formula, right? Now this is not directly related to this Q because Q is independent of the size of the formula, but it does say something very important. Then the formula is satisfied. Then okay, so that suggests that SAT in fact become easier as the clauses become bigger. But then, you know, Q side, some of the clauses might be small, some of them might be large, so we don't know. But anyway, SETH just says, you know, the formula becomes ridiculously hard once the clauses get bigger. And as I said earlier, it's probably, you know, it's the confidence it's correct is lower than the confidence that the edge is correct. Okay, so now the question is, what can we do with those two conjectures, right? And how can we make progress with them? So, so the first tool we are going to use is that one can sparsify formulas, right? So there is this specification theorem. So this is theorem 14.3. Specification And initially it's kind of hard to see what's the point of this lemma. So the point is that think about, I give you a formula, a 3-sat formula, or a Q-sat formula. Right? And it has way more clauses than variables, way more clauses. Than variables. Okay. So what this says is that we can convert it. We can convert phi into a new formula. It's going to be a big O of formulas. Phi I going to 1 to t, right? Now, the important thing is that t is going to be sub-exponential, right? So 2 epsilon of n, right? Here, epsilon is going to be epsilon is arbitrary here, right? So you can choose it, right? This is your constant to choose, right? So you choose how many variables you want. And the important thing is that the formula phi I are much more balanced. Phi I has n variables. In fact, they're going to be the same n variables as before, right? And epsilon n, sorry, not epsilon, k epsilon. K epsilon q clauses. Right. So there is some constant, some universal constant, right? This is a universal constant, and each one of those formula phi I is going to have essentially linear number of variable and a linear number of clauses, where the linear here, the constant, get worse as epsilon, as you change epsilon. But that's what the specification lemma says, right? Now, why is the specification lemma is interesting? Well, because it immediately implies the following important application. It says that under at the edge, a 3-sat formula with n variables and m clauses cannot be solved in time, you know. Right. So you cannot improve the running time. You know, the exponential time hypothesis essentially implies that the lower bound holds even when you take the number of clauses into account. Right. Okay. So that's that. Okay. Okay. To see why this theorem is correct, just you know, the proof is very simple. I'm not going to go into the low-level detail because they're not that interesting. But you know, just to put out that specification lemma didn't care about the number of clauses of the formula, right? So it enabled us to take a formula and dramatically, and reduce it to, sub-exponential number of formulas where each formula was balanced, right? Phi, where each one of them was balanced, right? So if we can somehow solve, namely for those formula, mi is equal to ni, is equal to n, right? So if this theorem, the claim of the theorem was incorrect, then we can solve each one of those formulas in time which is, small o of n, well, small o of n, let me maybe write it in more, small o of n plus m, n plus mi, but mi is of course just n because it's a balanced formula, so this is 2 small o of n, right? And now we have, what do we have? We have 2 to the epsilon n such formula. We have to do it for each one of the formula and take the OR. So, you get running time that solves the formula in 2 epsilon n plus small o of n, right? This is the running time to solve the original formula, but this contradicts each other. Right? So that's the proof of this lemma. Okay. So that's good. Another implication of a similar taste is the following theorem. Theorem 14.5. If SETH holds, then ETH holds. And this is an easy proof. You essentially take the reduction. One can easily show a reduction from SAT to 3-SAT, right? So if you give a CNF formula, you can convert it to 3CNF. This is, you might have seen it when you learn NP completeness. You essentially do padding with new variables and so on. It's not very difficult, and it doesn't generate. It's just increase the length of the formula by constant factor. So if I give you a set, if I give you a formula with q variables, you can turn it into a 3-SAT formula with a constant blow-up in the length. And as such, if ETH was incorrect, then SETH would be incorrect. And that's the end of the proof. Right. So that's easy. Okay, now a lot of NP complete problems are involving with graphs, right? But they have linear time reductions from 3-SAT, right? You get from 3-SAT formula, and in linear time, you get a graph which belongs to the problem, and they are satisfied if and only if, right? The 2 instances. So applying the same logic as above, we immediately get that if ETH holds, none of those problems can be solved in time better than exponential time, essentially, right? Formally, the running time of solving them is at least 2 to some constant times n plus m, where n is the number of vertices in the associated graph, m is the number of edges, and the list of problems is, what you expect, right? Vertex cover, dominating set, feedback vertex set, tree coloring, and Hamiltonian cycle, right? You just need to go through the standard NP complete reduction and verify that they're indeed linear, their output is linear size in the size of the original formula, right? And you can just plug it in. Okay, so the more interesting question is what happens if our reduction is not linear reduction, right? So for example, here's an interesting fact. 3-SAT can be reduced to planar 3-SAT. This is, by the way, a pretty surprising result. planar tree set. So what is a planar tree set? A planar tree set is you have a formula, but every variable and every clause has a node, and you connect two of them by an edge if a variable appears in a node, right? So you're going to get some graph. Let's assume this is right. You're going to get a graph that describes the formula, right? And the important thing about this graph is that it has to be planar, right? And the surprising thing is that you can do this reduction, right? So given a formula, given tree set formula of size n plus m, right, n variable m clauses, you can reduce it to planar tree set with, the number of the resulting graph has size n plus m squared, right? So you get quadratic blob, right? So the question, of course, is what can we say in this case, right? As far as at the edge, as far as lower bound from at the edge, and the intuition is that what we can get, we need to deploy the inverse function of the blob, right? So theorem. This is 14.8. If at the edge holds, then planar tree set cannot be solved in time better than, well, if it's of size n plus m, you cannot solve it better than some constant times square root of n plus m. Right. Essentially, quadratic, the lower one becomes much weaker, right? You give me a three-planar formula with n variable and m clauses, and this says, oh, you cannot solve it better than that. And I should comment that this is not hard to, in fact, realize. So there is an algorithm with this running time. Right, such an algorithm exists. It's essentially using the planar separator theorem. So that means that at the edge implies something useful, even if the reduction is not necessarily linear time, right? Even if it's a blowout reduction, and you get, you immediately get the various collection of such results for other planar graph problems, like, planar Hamiltonian cycle, planar tree coloring, and so on. I'm not going to go and enumerate all those problems. Okay, next we need to see how this, how at the edge is useful for fixed parameter tractability.